Problem 42, trapping rainwater. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. So this is the example image that they have, but I have another one here, so we can look at this one instead. So basically what should happen is we should compute the volume of all of this water that can be trapped here after the rain, right? So all of this will be flooded. So all this water, so we have to compute the volume of all that water. Now, probably the important observation to make here to solve this problem would be the following. So if you come to any point in this array, how would you decide how much water would be retained on top of this particular column? So if you think of this infinite, well, it should be an infinite column, yeah. So if you think about this infinite column, how much water would this particular column retain after the flooding? And I think it's quite easy to see that in order for us to determine that, what we should do is basically look in both directions from here and see where are the walls that water can be trapped by. So in this case, if you look right, we will bump into this wall. This is the tallest wall to the right. And to the left, we bump into this wall. So this is the tallest wall to the left, right? Well, hopefully these would be, not hopefully, but potentially these could be not necessarily exactly the same height. So this could be taller. So the important bit is for us to be able to, from each point, to be able to look to the right and look to the left and see where the tallest walls are from this point. Now, we could do this by having two arrays, right? So basically for each point, we could pre-calculate the maximum value that we've already encountered. So if we traverse this array first from left to right, we could remember where the tallest walls were that we've encountered so far. So that way we could build an array of maximums. So let's call that, let's say, max left. So max left, when we go to 0, that would be 1 because it's 1, right? And then it's still 1 when we come here. And then this is 2 and still 2, 2 again. Here we get to, let's say this is 4. And then 4 again. And it will just forever remain. So it will be 4 all the way down. And then we could traverse from right to left and do basically the same, right? So potentially we could do max right. And we could calculate the same 1, 1, 1, 2, etc. So once we have these two arrays, right? Max left and max right. So these will be arrays. And then we could do one more traversal in either direction. Doesn't matter which direction we do it. So, for example, we could, let's say, we could travel in this direction. And at any point, basically, what should we do? We should look at this point for example, and identify the height of the wall to the left. That would be max left. The height of this wall, max right. Then we would identify the minimum out of these. That would be the level of water, right? If we identify the minimum, that would be this here. That's where the flood level will stay. And if this is the level, we could then subtract from the water level the value of this particular height. So here it's 0, but I mean, it could be anything. Okay, so it could be absolutely anything. So in this case, this is 0. So we would subtract from the level 0. So all of this column, the entire column, would be flooded. Now, just think about the following for a second. When we calculate maximum to the right or maximum to the left, that will also include, at least the way I'm going to do it, that will also include this particular value that we are looking at. So let's say we are looking at number 5. Okay. So maximum to the left will be, in this case, would be this value itself, which is 4. So maximum to the right could also be the same value, but let's say there is even taller, just in case, let's say there is an even taller wall here. So maximum to the left could be even taller, so it's 5. When we take the water level, which is the minimum of those two, that would be 4. And then we would subtract this entire column, which means at this point we would correctly calculate 0 units of water volume being retained at this point. So what I'm trying to say is, in this kind of edge case that we have to ensure that our algorithm performs correctly, because we're going to calculate max left and max right, including the position, the index where we're looking at, this still gives us the correct calculation with the algorithm that we just identified. Okay, so I think we can proceed with this and we can try to code what we just discussed. So we will, okay, so first of all, we're going to do max left, right? Let's do max left, and we need an array for this. So how do we do that? Let's create that array first. That would be a new array of type number. Number of elements here would be same as height. So same as number of elements inside height. And then we should technically always fill it with something. But in this case, I know what we're going to be doing with it. We'll actually be filling it. So let's not waste processing time with filling this, because we know what we're going to do with it. So in order for us to put maximum values here, let's do a little loop for let I be the first element with index 0. Okay, and then obviously I should go to all of the elements to, well, let's try that we are actually traversing height length. It's the same thing. So obviously height length and max left length is the same, but we're traversing height array. So I'm going to put that. Now here I will need a temporary max left value. Even though I'm creating an array, why don't I just have a value max left? I mean, you could do this in different ways. This is not a very complicated thing to do, but I'll just do it in this way. So I'll keep the running maximum in here. I could also always look in the previous element, in which case I could initialize the first element. So I could do something like max left 0 is set to height 0, in which case I need to be sure that that element exists. So max left array is not empty. And I think we are given that assurance here. So we have at least one element, but I mean, I still, if I want to do this, then I have to do some sort of assertion that actually that element exists, or, you know, so just to avoid that, I'm going to continue. I'm going to do it this way, right? So this will work correctly whether heights array is empty or not empty. So now what we're going to do is we're going to update max L would be maximum value of itself and the current height, right? Height I. So that's the maximum value, but then we also need to store this inside max left array, right? So that should do it. So we traversed this in one direction. Now, technically, we would be traversing this in the other direction as well, creating the max right array. But so now we would be traversing in the other direction, creating the max right array, and then we would be doing another traversal. And we said it doesn't matter which direction. So why don't we combine the second and third traversal in one? Right? That's what I'm going to do. So I'm going to combine the last two traversals. So as I am calculating for each spot, I'm calculating what is the tallest wall to the right. Now I could simultaneously, well, not simultaneously, but just right after getting that number, right max, I could also just look into the left max as well and do the calculation that we mentioned, you know, the level, water level, which is the minimum of those two maxima, and then, you know, the column of water that is retained above this particular index. So I will try to combine these two calculations. This may not be the most readable code, but perhaps because LeetCode measures the speed and efficiency, maybe will perform slightly better. But again, this won't be optimized for readability, right? So we'll be traversing in the opposite direction, right? So we'll start with height, length -1. And then I would be, we need to traverse, well, actually, we don't need the last element, because the last element with index 0, it's never going to retain any water. Whether it's tall or not, it's never going to retain any water. So we can ignore that last element. That's the beauty of running loop manually. I mean, we could always do reduce right or reduce, but that allows us far better control for cases when we need to optimize for speed a little bit. Okay, so we're traversing from right to left. Now, we need to have the maximum, right? So we need to have max right in this case, and that is minus infinity for us. So let's now, first we're going to calculate max right. So this will be the maximum value of itself, and height I, correct? So this should look, they should look almost identical to this, correct? So now we have max right value. We can now calculate the water level. That would be minimum between this max left I and max right. Well, this we'll retrieving the max left from an array, but max right, as we said, we're not going to actually create an extra array for this. So that's our water level. Now, technically, our delta V, which is kind of the column, the volume of water just above this index point, would be what? It would be the water level minus height of the current current elevation. And then we need to add this to some sort of total. And the total would be, let's say volume is 0, and here volume should get updated by this dv. But I mean, we could just, this dv is not very clear what I mean by this. I think if I write it like this, it's just as clear. I mean, we could turn this into just a single line, obviously. So max r we could just copy this over into here and then just turn this whole 3 lines into a single line. But I think that would impact readability. This is probably the clearest and shortest option that we could do, right? Here we just return volume and we should be done. So that is our function. We can try to see whether this actually does what we need to do. Okay, the pretests were passed. Let's risk submitting this to the actual full test suite and see what happens. Okay, so we passed. That is excellent.